Hello everyone, and thank you for joining us today for the College of Engineering Faculty Lecture Series. The 2024 College of Engineering Faculty Lecture Series features lectures from faculty members leading groundbreaking clean water research in the areas of wastewater recycling, desalination, mineral extraction, water quality management, and more. Today's lecture is titled From Brine to Mineral, Extracting Minerals in Clean Water from Brines Using a Thermal Cycle and Machine Learning-Based Design. The lecture will be presented by Dr. Bahman Abbasi, Associate Professor of Mechanical Engineering. My name is Sabayatha Satish Kumar. I'm a student in the College of Engineering, and I will be today's event moderator. We encourage you to submit questions throughout the lecture using the Q&A button at the bottom of your Zoom screen. A recording of the lecture with captions will be provided to all audience members after the event. If you need assistance at any point during today's event, please put it in a private chat to the host and moderators. With that, it's now my pleasure to introduce Andy Dong, School of Head of Mechanical, Industrial, and Manufacturing Engineering.
I am pleased to introduce today's faculty speaker, Dr. Bahman Abbasi. Bahman's research addresses the water-energy nexus, including control systems in thermal fluid applications and advanced metals and materials. He has authored 20 technical publications, including 5 issued patents. 2 of his patented technologies use the process of humidification-dehumidification. Bahman and his collaborators are deploying them in 2 clean water applications. In one application, they are removing contaminants from water polluted by industrial processes, such as hydraulic fracturing, mining, and agriculture. In the other application, they are developing a desalination technology that does not require complex infrastructure or lots of energy. Their desalination technology is poised to help the world secure more lithium, the increasingly scarce metal used in rechargeable batteries, powering everything from earbuds to electric vehicles. You'll hear more about this in a moment. Bahman, thank you for joining us today. I look forward to your presentation. Over to you.
Thank you very much, Andy. My name is Bahman Abbasi, and it's my pleasure to be here today. Thank you very much as well, and thanks to the audience for being here today. So today I'm going to talk about our research over the last several years, and I will talk about the scientific aspects, the practical aspects, and a lot of things that go after the research is done and is completed. So let's get started. We will talk about the problem. What is the problem that we are trying to address here? What is the research looking like here? And some of the results. I'll present that to you all. And we will talk about technology development. When the results are published, it's all done. What all goes on in developing technologies, and then the outcomes. So one embodiment of our technology, the big problem with lithium and electrification. As you all know, we are transitioning to a greener, electrified economy and energy sector. And that comes with a lot of consumption and demand for lithium and battery storage. So where does all of this lithium come from? Several methods. One is what we call hard rock mining, different discussion for a different day. One is from brines. So if you look up here, in a lot of volcanic areas across both South and North America, we have these continental and geothermal brines that they have dilute amounts of valuable minerals, especially lithium. So what extractors do, they take the brines, these are subsurface brines, they get them out of the earth, and they put them in these solar evaporation ponds. This case, somewhere in Bolivia, 4,100 square miles of solar evaporation ponds. Absolutely enormous. This is one of the largest in the world. And because these are so dilute, it is really not worth extracting lithium from unless you concentrate them. So they sit here for a year or 2 years, and they naturally evaporate the water away, and they start to concentrate until it becomes economically viable for them to extract that. Immediately, you can see some problems with this, right? One problem is we are in arid environments in these locations, and you get this water out of the ground and you evaporate it away. You have a long lead time. There are other problems we will talk about later in the presentation. And the other thing is that there is increasingly emphasis on having supply chain security for our transition to a cleaner energy. And this is where we come in. So how do we want to address this problem? Number one is just like in South America and in China, there are a lot of these brines. Here at home in the US, we have a lot of these brines as well. A couple of problems with that. Look at the concentrations here. In Clayton Valley in Nevada and Salton Sea, among other places in the US, our initial concentrations of these valuable minerals, especially lithium in this case, are relatively low compared to those in South America. They start with a few hundred, 300, 400, 500 ppm, and we start at about 200, 150 down to maybe 1800 ppm. So we need to do a lot more concentration here. The other thing is that because we have a lot more stringent environmental laws here, we cannot just evaporate the water away, which is why in the US we have the one plant in Silver Peak, Nevada that does the solar evaporation pond. And that presents an opportunity to step in and do this in a more environmentally sustainable and responsible way. To tell you what part of the overall process we address, to really simplify lithium extraction from brine, we have the source, we get it out of the ground, there's some chemical pre-processing, it's not very extended, there's some. And then, by and large, the most time-consuming, expensive, and surprisingly, polluting part of the process is the solar evaporation pond. These red shapes you see, these are thousands of square miles of solar evaporation ponds. And then when it really concentrates, there's a chemical post-processing to get lithium ions out of that solution. So where we step in is step 2. The longest, most expensive, and most polluting and most environmentally damaging part. We have this technology is a once-through process that relies on low temperatures and and an evaporative cycle, just like Andy described, to achieve the same thing, obtain clean water instead of wasting away the water, produce solid salts, and produce a concentrated lithium brine from which we can extract lithium salts suitable for battery manufacturing. How do we do this? This is a little wordy, sorry about that, but this is the prototype that we built and demonstrated in the laboratory. This is what we call an air blast atomizer, and the way that it works is it gets a film of brine down here in the chamber, so we have low concentration brine coming in, and it is blasted by relatively low pressure air. So when you do that, it's just like blowing on a bowl of soup. You start spraying things everywhere. And that's the goal. When you spray that, you have a good opportunity to start condensing and evaporating these things. So these droplets go over the heat exchanger here, and they absorb some heat, and they move up because of the momentum of the flow. And as they evaporate, a couple of things happen. Your air becomes very humid air. So up here you have a lot of humidity. The other thing is you have initial concentration of sodium, potassium, a whole bunch of other salts that as you concentrate and evaporate, these oversaturate and they create flakes. Sodium chloride, potassium chloride flakes. And these flakes are small enough that they just get blown away to this cyclone over here, where we extract almost all the salts, and the humid air without salts come here. We do some thermodynamic adjustment, goes through the heat exchanger, where it rejects its heat to the outside, helps evaporate things, and condenses the water out. So what do we get out of this? Number one, lithium-free solid salts. A bunch of salts that come out in solid form, and I will tell you what the value of that is in a moment. Product number two, humid air that comes out, we condense the water out and becomes clean water product. Number three, we get this unevaporated portion of the initial brine that is much richer in lithium content, and that is suitable for extraction. This process is patented and granted under 2 patents. And this is how, instead of wasting the water away, we get the clean water and we get the lithium. And what happens to these salts that I talked about? There are a number of things you can do with this water. One is for local uses, irrigation, agriculture, what have you. The other one is because these are very delicate ecosystems, it is really critical to replenish these aquifers. So one thing you can do is take the water, for pH adjustment and composition adjustment, you put the salts back into it, the ones that you don't really need, like sodium chloride and things like that. Put it back where they belong. So all we've done, we've taken this sliver of water with valuable minerals out of it. Let's go through some of our results, some of their process before we talk about the technology. One is for anyone who's worked in this kind of environment, this kind of thermal fluid environment full of saline and high salinity solutions, salts everywhere, fouling everywhere. And one of our biggest tasks over the last several years has been how do we mitigate and prevent all this fouling? Case in point, we have a few major components. You know, the atomizer that I talked about, the cyclone that I talked about, and the heat exchanger. Let's look at the fouling in these three. This is a conventional air blast atomizer. We ran a 20% saline solution through it. That means 1 part water and 0.2 parts of salt. That is about 7 times saltier than seawater, 7 times saltier. This is a time history graph of mass flow rate and pressure. All these fluctuations is when you have clogging in the nozzle. It clogs up, increases the pressure, reduces the mass flow rate, and the flakes break off, and then releases some, and then you have clogging all over again. And that's what happened with a traditional air blast atomizer. Our air blast atomizer, you see almost no variation over time, which means that we entirely prevented and suppressed fouling in our system. The other place is the cyclone. Cyclones are not made to work with humid streams. They've been around forever, mostly with dry streams. So it was really important for us to operate this without salts accumulating all over the interior of the cyclone. It was equally important to get almost all the salts out, because then we can desalinate water and use it for even potable applications. So we ran this, and this cyclone is what you see after 1 hour with 80% salinity. So we're talking about 0.2 parts water, 0.8 parts salt, oversaturated with salts. After 1 hour, no evidence of fouling. There is no fouling whatsoever, and we can talk about why and how. And this is what comes out of the cyclone. It is by mass 95% salts, meaning that almost entirely dry salts, so we don't lose a lot of water. And we've run this with so many different salinities in a once-through process. We can get almost all the salts out of it and desalinate the stream. These salts are usable. Some of them, like potash, can be used for fertilizer and other applications. They can be used for thermal storage. They can be sold, or, as I said, they can be mixed back with water, put back where they belong. The other thing that we did, the heat exchanger part. Heat exchanger, by nature, because we have an evaporative process, it is fertile ground for fouling. Anyone who's worked with heat exchanger in cellular environment knows that it's just a nightmare to work with these things. So we invented this heat exchanger, and we did a lot of experiments. When we have evaporation rates of 90%, meaning that not 90% of the initial mass is evaporated, we almost entirely prevent fouling. But when we go further higher, over 100% evaporation, then you start getting some fouling. That's almost inevitable, best I can tell. But the good thing about our system is that we can then in situ flush it with clean water for a few minutes, in this experiment 7 minutes, and wash it away, go back to point 0, and continue the process without ever stopping it, without ever compromising anything except for time, 7 minutes about. So these are the component level things. Then we obtain this tote that you see here from Clayton Valley, straight out of the ground. We did an ICP analysis of it. It has about 230 ppm of lithium, and this is what we used in order to examine the efficacy of our system for real, untreated lithium brine fresh out of the ground. I can go through this in some length. So let's start with water only. There are a number of things we need to address in a system like this. Number one is we keep talking about evaporation rate, concentration. How much of this stream can we evaporate, and how controlled can that be in order to obtain the desired level of concentration? So we started by doing water only, and we demonstrated that between 40% evaporation to full 100% evaporation, we could control that. And this is rather recent result, about 1.5 years ago. That gave us the first knob, controlled evaporation. The second one is now we want to see, okay, if I put something else in this water, do I actually get to concentrate it? And when I concentrate it, what happens to the ions? What happens to the salts in the solution? So we synthesized the solution, put lithium chloride of different concentrations in it, and we started running our experiments. Controlled evaporation, you know, when you have lithium brines, doing 40% doesn't really do anything for you. You have to go much, much higher than that. So we did about 70% to about 98%. What did we learn from that? Number one, if you go to 100%, it means that all the lithium chloride you dissolved in it, you've evaporated 100% of the water out, so you get all the lithium chloride back. So basically, you haven't done anything. It is really important to leave some in the solution. So that's why we stopped. It's really critical for us to stop at a certain level. In this case, we showed that we can stop at 98% if we wanted to. The other thing is that we have to do this with minimal to no fouling. And that was another critical point that we showed that we could suppress all the fouling. And now we get to the really tricky part of all of this, which is lithium loss. Okay, so in brackets here, those solar ponds that I showed you earlier on, they basically just sit there. And over 1 year or 2, as much as half of the lithium content makes unusable salts, sediments, and goes away. So you can never really access or extract that in any economical fashion. So they lose half of their lithium content to undesirable salts, primarily lithium carbonate, or lithium chloride, sorry, lithium chloride. So it is really paramount for us to duplicate this process while preserving water, lower energy, lower cost, but also cut the lithium loss from the process. Instead of 50%, whatever we save, we're in good shape. So we put fresh brine from Clayton Valley into our systems, and we demonstrated controlled evaporation between 60 and 93% and no fouling. And then we showed that we can dramatically reduce lithium loss rate at various evaporation points. So I'm not going to talk a lot about this plot. This plot shows an average of what a typical traditional solar evaporation pond, what we call a salar, does. And those at about 70% evaporation rate, those salars lose about 38% of our lithium. So at 77% of water gone away, 38% of lithium goes away. We did the same thing in our device, and we cut the lithium loss to just about 16%, or less than half of what it is. Is 77 good enough? Not really, not quite. We are targeting going from 80 to about 90% evaporation rate as a starting point for our initial pilot plant. And then we want to make sure that we demonstrate, we do the research to maintain a low lithium loss. The reason that we stopped at 93% was honestly because at 93% we started losing a lot of lithium and the experiment started becoming meaningless. So we came back down, and now we are actively conducting the research here at OSU to see how we can control the pH, how we can add chemicals in order to adjust that and move from about 77 to 80% and to 90% while maintaining a low loss rate. Now we've done all of this. We've done all of this. We got the Clayton Valley brine. We concentrated all of this. And the last step that we need to show for the complete validation of our work is, okay, you have this concentrate from your system. Can you actually make battery-grade lithium salts out of that? Which is what we also did. Credit goes to Dr. Scott Geddes at OC Cascades. We produced a solution and multiple steps that he can explain a lot better than I can, and a few steps of drying, and he helped us produce near 100% purity lithium carbonate, this compound, which is a key compound from which lithium-ion batteries are made. So we showed that we can do all the concentration as well as all the extraction. And that put us at the place that, okay, our research seems to be working. What are we going to do with this? In order to take the next level, take the idea to research, which we did, and take research to a technology, we started a company. We started a company, SPQ. It's a water and mineral extraction company. And whenever you get these slides, our videos on the technologies are over here. And we took the next step to develop this and make this into a technology and product. So fun fact about this, this little clover that you see, our logo, it is actually a water molecule. These are the hydrogen-oxygen bonds, and these are the free electrons. This isn't for the chemical engineers and chemists among you, sp3 hybridization molecule, and it's a little Easter egg that we've hidden in our logo. So what did we do through the company? Let's move on to the technology development side of this. In order to get this research and make a technology out of it, we needed to address a lot of practical engineering things. Make a lot of busy, crazy-looking diagrams like this one, full of flow loops, actuators, sensors, size your pumps correctly, size your pipes correctly, source the right material in the right place for the right application, all the elbows and T's and joints, measure your pressure and your temperature and flow rate with the right kind of instrument in the right location. Not only that, get all the data and through your data acquisition system, run a control algorithm on it to make sure that you can control all of this. So a lot of detailed engineering work in building a system like this. So we designed a full fabrication-ready engineering system of this that could handle, or is projected to handle, 2.5 tons per hour of brine in a 40-foot container and produce about 72 kilograms of lithium carbonate per day. And I will come back and tell you what those numbers mean and why they matter. But before that, let's look at the container of ours. A very distinct feature of our technology is its modularity. So a few slides ago, you saw our bench scale technology, what it looked like. Now, these are just the bigger versions of that. So in this system, a top view and an ISO view, you see 3 rows. Each row has 4 modules, 1 module, 2 module, and 2 under them. So 12 modules in 1 unit. What's the advantage of that? Many, many advantages of that. Number 1 is if you have a giant operation, you can have more modules and scale it up just about indefinitely. Number 2, if you have a smaller artisan operation, and some of these are much smaller, you don't need a permanent fixed plant for a long time. You can take a container that will match your need, your production needs, and take it to the site, deploy it on the site. When its usefulness is done, take it away. The other thing is that you don't even often need the container. We have a design, I will show you the design, that has just the 1 module. And that module, it can do lithium, it can do water desalination from just about any source, and it can be deployed anywhere you want it to. So, long story short, we took that flow diagram that you saw in the last slide and turned it into this full-fledged CAD design. And this one is a little reduced in complexity just for visual, but you see all these pipes, connections, flanges, everything is independently designed, sized, and analyzed to handle all of our flows and pressures and what have you. The next step, now we have these designs, we have a company, is a lot of things that as a faculty I did not foresee doing when I started this, making the economic case for our technology, making really the case that who outside of a research organization would want to invest in this and help us develop this. So we had this extensive effort to really justify, okay, our research yielded results. We think we can make this technology work, but we need to convince investors that the economics at the end of the day are there. So I told you that I will come back and tell you the meaning of those numbers. So 200 or 2.5 tons per hour of brine, depending on what the initial concentration is. I said we can produce as much as 72 kilograms per day of lithium carbonate equivalent. That is when you start about 200 ppm of lithium. 72 kilograms. We did a lot of work, years of work on our techno-economic analysis. So everything that I've shown you, cost of heat, cost of material, cost of engineering, cost of staff, cost of permitting, what have you, cost of financing, all of that went to a model that told us our levelized cost of production for lithium was just under $3.50 per kilogram. $3.50 per kilogram. For reference, the latest published numbers on that number is the average production cost in both North and South America is about $5.8 per kilogram. So we come out below that cost, which gives us big advantage. And based on that, we can look at projections for what the price is going to be. So in 2022, they peaked to some. It expected to continue through 2026 at about $40,000 per metric ton or $40 per kilogram, giving us a huge headway for marketability of the product. So based on that and all the models we analyzed, and we could estimate that each 40-foot container can yield just under $1 million per year of profits, not cost, but profits. And this is the kind of analysis, this slide, this one thing took us years to develop. And this is one of the key things that we need to tell and show investors in order to get to the next level. What is the other thing that everyone wants to see is, okay, you do all of these things, but who else is working on this and what are they doing? This is a very busy slide. I just want to tell you a few things about this. So whenever, it's just like doing research. When you want to do new research, you go and do a literature review to make sure that who's done what and when and how you can build on top of that. Building a company, building technology is much the same way, except that people don't publish their work in journals. So it takes a lot of effort and a lot of really study to piece together information about who's doing what and in what space, and who you can approach and with whom you can talk to get really industry feedback. What is it they're looking for? So in our case, for you all's knowledge, the primary competition for us is solar evaporation ponds. Solar evaporation ponds, they've been around for a long time, decades upon decades. What's good about them, they're passive, they're mostly low maintenance. When you dig the thing out and prepare it, you don't need to do much about it. Cons, like I said, it's a batch process, takes a very long time, immense land use, immense losses, immense environmental losses, what have you. Secondary competition. There's a pilot plant being built, being commissioned the next couple of years by a big company with multi-billion-dollar backing in Lilac. They use a different technology. It's called ion exchange technology. Very simply, they exchange a certain kind of ion for lithium ions. So they get lithium ions out of it, and they replace it with some other ion. In many cases, it's hydrogen ions. And pros and cons, they don't waste a lot of water. They don't waste a lot of land and resources, but they have fouling issues. I told you, when you work in these brines, you have a lot of fouling problems. And there are a whole bunch of other technologies in the work. Nanomembranes, absorption, desorption, electrodialysis. I tell you these things because it is really important to distinguish between various technologies. Fouling is a huge deal. As soon as you have a packed bed, as soon as you have a membrane, as soon as you have a bead, like absorption-desorption systems, you will have fouling issues. In our system, because we flow the salts out of the system, we don't accumulate them on a membrane. That's a huge advantage for us. The other advantage, which is why I put this slide here, is our technology does not go and do something entirely new that the industry is unfamiliar with. The point of emphasis here is this industry has been around for a long time, and we are trying to build a technology business. So now, if I take this technology business and just do it completely different, just the adoption time changes a lot. Our technology does not have that shortcoming. It will work with the pre and post-processing, and it will just replace and duplicate that evaporation process without the damages. So some of our advantages: we produce the 3 products, the lithium brine, clean, usable water, and salts. It is low temperature, which is a critical thing, because if you have high temperature, high pressures, then you have specialty materials. The cost of construction goes way up. Our materials are so low cost. Our operating cost can be low cost because we use low-grade heat, because we use low-grade water. And of course, fouling prevention. Now, just recap real quick. Idea, research, technology, it works. The economics are there. We have done our market analysis, our competition analysis. Now, the next step in all of this is market acceptance. Who is working on this? What does the timing look like? And is this the right time for this technology? This is one of the last and really, really critical steps in any product development, technology development projects. So we commissioned a study to see various large and small businesses working in this field and how we can find our footprint within this space. So again, I'll show you this because these things are not published that easily. It's not like you go open Elsevier and you come up with this stuff. Our contractors had to pour over state and federal data, public SEC filings of different companies to understand who's doing what and how, and a lot of digging to see, okay, these are the big companies, they're building such and such plants, these are the filings based on the filings, these are the timelines, and now this gives us as a company a chance to align ourselves with certain entities at certain times. For instance, one of the things that we are trying to do is the biggest lithium mine in North America is under construction in Thacker Pass in Nevada, in northern Nevada. And the construction phase goes through about mid-2026, and the phase 2 starts after that. So what we really want to do as a strategic maneuver or strategic partnership is do our pilot plant in the next year or so, and then start integrating with these upcoming plants, because unlike, let's say, smaller high-tech, these mining operations, these extraction operations, they're not for a year or two. They build something, it is there for 4 years. And if you're not in, it takes a very, very complicated effort to get into this. So the timing is a big part of it. With all that said, where are we today? So the research is done. The prototype is complete. This is our bench scale, which we produced and demonstrated. This is going to be our first, what we call skid, our first prototype, fully contained prototype. It is about 5-6 feet by about 3 feet, 4 feet tall. It can process about 100 kilograms per hour of brine. It is self-contained except for the power source, so we need to bring in electricity and power source to operate this. And all the parts are ready in this one. Everything has been machined, everything has been ordered, a lot of it is in the lab. We're going to assemble this, operate this, run it, and we will do that in the next couple of months in order to show that this system can work. And then we have the funding, we have the resources and the plans, as I showed you, to build our first pilot, which is going to be a 20-foot container. When we build it, it's going to be done sometime this fall. We'll take it to OSU Hatfield, where we will test it, initial testing with seawater, desalination application, and then we'll take it to Reno, Nevada, where a lot of these mining operations are working in order to be able to demonstrate this on-site with the real brine. Something else about what it takes to do all of this. So I put this slide here because to get this far, to build all of this, it takes an army. In this case, both the figurative and the literal US Army, which is our biggest backer at SPQ. This has been a collaborative effort between University of Nevada, Michigan State University. A bunch of organizations have funded us, the US Department of Defense, the US Department of Energy, private enterprises, and the state of Oregon. And a bunch of companies, so who designs this, who fabricates this, who tests this, these are all very disparate skill sets that we had to bring together over the years. And I put something else down here in bullet points. I just want to emphasize this because as I'm now the CEO of SPQ, as well as being an associate professor of mechanical engineering, these things that you see here is the things that I deal a lot with: accounting, bookkeeping, tax accounting, legal, HR, benefits, recruitment, program management, fundraising, and all these things. And it is all essential parts of taking your research and making a product out of it. And at this point, our team has put a lot of time, effort, and energy into creating all of this infrastructure for us to be able to get to this point. Something else about the outcomes. I kept one of the most important aspects of this work for last, and I want to just spend a couple of minutes talking about this. What I showed you has been going on since 2017, and it's taken an army of students and colleagues to do this. So I kept this for last because the people you see in this slide, they were instrumental in all of this. Our students are really the lifeline of this university, this research, and all of this. So huge, huge credit to all of them. The guys you see here, some of them are co-inventors. We graduated 4 PhD students, 6 master's students, nearly 24 undergraduate research assistants, 3 postdocs. We published and acquired 3 patents based on this technology. 20 journal articles, every last one of them was a lead author, was a student or a postdoc, not a single one of them was me, and dozens of conference publications. Some of these students I hope are online. This work has a lot to do with you, and I thank all of you for this work. The other part, we have been able to get the word out through an engineering podcast. If you have any questions, any thoughts, email me on the SPQ side or on the OSU side. And I think I finished about 5 minutes early.
Thank you, Professor Abbasi, for sharing your research with us. It was very interesting. I have a couple of questions, and we'll now begin our Q&A portion. So you talked about how you did your small prototype, and now you're going to be building out your pilot in 2024 June, right? So how are you able to kind of get those numbers? You said 2.5 tons per hour, 72 kgs of lithium. How are you able to get those data points without having built it? What are you using to predict those numbers?
Excellent question. So a few days ago, I gave a talk in a relevant area, and a colleague asked me, what was the hardest part in building these? What is the hardest part of this outside of the technology part? I said, acquiring the data, finding who's doing what and how. So these numbers that I show you, these are not just calculations, and that is really important to point out. So there's a lot of simulation that goes on into this. So just like any research, this is business economics research. You need to find your assumptions, validate your assumptions, and you need to be able to collect those, build the models, and predict a result. But in this case, that's not where it stops. These results need to be compelling enough for producers, for funders, for investors, for consumers, for them to be interested in it. So what I like about your question is it really shines a light that the first time you run this, this is not the number that you get. These are design points. You get a number from your economic analysis, and then you have to go through and say, okay, how can I go and improve upon this number? What part of my technology do I need to change in order to get more yield, get lower cost? So when I show you 12 units in this, that is not a coincidence. That was not where we started. We started with 10 units. Yeah. And we ran our numbers. It was not enough throughput in the system. It was too big. The cost numbers wouldn't work. So we had to go back. These units did not look like this. We needed to adjust the technology, adjust the number of atomizers, adjust the flow rate through each module, redesign the whole thing in order to find a different form factor, in order to be able to come back, run the numbers again, say, do we have enough flow rate through this now? With that flow rate, what kind of numbers, what kind of cost we get out of that? And we kept doing that in order to come up with something that is doable, technologically sound, as well as appealing to customers.
Okay. And then I guess my second question was, you mentioned that solar ponds are quite passive and that they just kind of sit there for years. How do you foresee the maintenance of your product and the longevity of it, and how often you'd have to maintain it and things like that?
I feel like I'm pitching to an investor, so I get this question a lot, and it's really one of the first questions that any operator will ask you is that, okay, what are you going to do with maintenance on this? Excellent question. It is one of the key costs, one of the key things that you need to be able to address in order to advance your technology. For that, I'm going to go to this slide. So maintenance is a huge part of any operation. Mm-hmm. If you have too many moving parts, if you have too many really specialty things, this and that, it's an operational nightmare. So from the outset, one of the really constraints, boundaries we put out for ourselves was we are going to minimize the number of our moving parts, because moving parts, generally speaking, suck. And we are going to find a way to lower our costs as much as we can from the maintenance side. So our costs are going to be, we do have a moving heat exchanger, so we want to get away from it. We haven't yet, so those, let me show you here. This thing, this is our heat exchanger. It does move. That's how we prevent fouling. And it's taken some effort to seal this, to do it the right way. We want to move away from it, but we haven't yet. At any rate, so our maintenance costs, let me go back here. Our maintenance costs are to make sure that we mitigate our fouling. Our temperatures, our pressures are pretty low, so the longevity, durability of our materials are very, very long. And because we take fouling in situ in real time, it's not a batch process, there is minimal involvement in an operator. The operator doesn't need to be there to go and get the membrane out, replace the membrane, do things like that. And that the same cannot be said about a lot of our competing technologies. For instance, if you have a membrane treatment, there are a lot of really good membranes out there and low fouling membranes, and they can backflush things, but the operation costs a lot. Mm-hmm. If you have really high pressure, high temperature processes, the longevity of materials, the maintenance schedule of materials are very, very different. So long story short, yes, we do have maintenance costs. Everybody does. It's a point of emphasis for us to make this simple enough, as much off the shelf as you can, and design it with such a thermodynamic process they need minimal maintenance involvement.
Awesome. Thank you so much for answering my questions. I'm going to move on to the audience questions. And remember, if you'd like to pose a question for Professor Abbasi, please submit it using the Q&A button on the bottom of your Zoom screen. We had some advanced questions submitted by the audience members. We won't be able to address every question today, but we'll get to as many as we can. So we'll begin with a question right over here. To your knowledge, regarding replenishing the aquifers with the water and salts, are there any organisms that depend on lithium?
Excellent question. I do not know the answer to this. It's something I need to go figure out. Part of the answer is if you have certain kind of brines, that is very unlikely. So in the very beginning of my talk, I said continental and geothermal brines. There are two different kinds of brines. Continentals are usually a lot lower temperature, mostly in the range of, I would say, 50, 60 degrees Celsius. Geothermal brines are pressurized. They are in the range of 130-ish Celsius. It is very, very difficult for a lot of organisms to survive in that environment. So if our source comes from geothermal brine, it is very unlikely. From continental brine, I do not have the answer. I will find out the answer.
Okay, let's move on to the next question. Can you use this process to make desalination for potable water more affordable?
Thank you for whoever asked that question. That's a great question because, so this is the thing that I did not emphasize in the beginning because this is a lithium talk, right? So this whole thing, let me go back here. There you go. There you go. This process was not conceived for lithium or minerals. It was not even on our radar. We started by developing a water desalination process. The whole genesis of this work, all the students that I showed you, their project was water desalination. We wanted and we invented a system that could take any salinity water and produce potable water, whether it's seawater, what's reverse osmosis discharge, whether it's water from Red Sea, whatever that is, in a one-through process and make potable water. And the answer is yes, we could do that. We did do that, and it was great. Then I'm just gonna tell you where this lithium thing came from. We wanted to do a zero liquid discharge desalination because concentrated brine that comes out of desalination processes, that's very environmentally damaging. They disperse it, it's costly and all the rest. So this has no liquid discharge, solid salts and just water. While we were doing that, we were struggling to evaporate 100% to get to zero liquid discharge. And around the same time, we happened to see that, oh, there are people who actually just partially want to evaporate things, not 100%. So the thing that we were struggling to accomplish turned out to be our advantage in order to partially evaporate and get a concentrated solution to do something else with. Just for y'all's information, we are actively looking at potable water applications. We have proposals, we have projects ongoing to apply this for distributed potable water application for military bases, disaster areas, refugee camps, what have you, where you don't have a lot of infrastructure. That is really near and dear to us. If you listen to our Engineer Out Loud podcast, you will hear all about that. And that was a great question, gave me the opportunity to ask this.
All right, next question. What is the estimate of, I'm guessing, kilowatts per hour?
That's right. So I can answer that in two ways. Number one is, as a faculty, as a professor, I am very, very comfortable saying that the theoretical thing that we can achieve is 37 kilowatt hour per metric ton. The things that we most project right now is 54 kilowatt hour per metric ton. But as the CEO of SPQ, that is our trade secret, and we should not disclose that number, which I just did.
All right. What keeps the outside of the HX from fouling?
Great question. The rotational motion. So this is the heat exchanger right here. We did years of study on the root causes of fouling. Just to give you a little bit of context, fouling has been a research topic for many, many years, and different researchers over time have come up with different root causes of fouling. And we did the same thing for our line of work. In our particular system, what is it that causes fouling? We identified those, in our case, 3 reasons. And one by one, we designed our system to eliminate those. Number one is high surface conductivity. If you have something that is very, very conductive, your substrate, like aluminum, which is, by the way, this shape, high surface conductivity causes fouling. Number two is rough surfaces. If you have a rougher surface, you create nucleation sites for salts. And those nucleation sites create some unevenness in your heat transfer and create that. Number three is when you have dry spots. And that's really the answer to the person who asked the question, is if you have a spray and the spray goes and it evaporates on a surface, over time, because of that evaporation, doesn't matter what you do to it, you will start getting some salts on it. The good thing is that the same spray carries a lot of fresh water that can also wash the water. So if you have a steady state system, non-moving system, you keep doing the same thing on the same spots. Some spots are perpetually wet, some spots are perpetually dry, and you start building it up, which is why our heat exchanger actually rotates. It rotates at a rate of about a quarter of a rotation per minute, so it's very, very slow. But even this slow rotation allows for a tube that was here and was about to foul up, starts moving up, and gets exposed to other environment and slowly washes away. So long story short, and we have a journal article on this right now under review, if you take the same geometry, you don't move it, in less than an hour you foul it up, it doesn't do anything. If you move it, you can just about mitigate all of that. So long story short, from a scientific standpoint, identify the root causes, design around them, and operate in such a way to mitigate it.
Awesome. Next question we have is, do you think employment of microchannel heat sinks would improve the thermal cycle of lithium batteries?
Absolutely. So microchannels are great in many aspects, many respects. I did a lot of heat exchanger design, heat exchanger development, not specifically microchannels. There are a few problems with microchannel heat exchange. I have to qualify this by saying that I'm not a battery guy, so what I say about batteries, take it with a grain of salt. But generally, if you have an ionic solution through a microchannel, if you have phase change through a microchannel, if you have a low pressure system through a microchannel, you start running into some difficulty. So microchannels, by nature, they have a large pressure drop because you have a lot of friction with surfaces. Now, if to that you add phase change, evaporation basically, with a saline flow with a lot of salt, you have a lot of crevices, a lot of nooks and crevices in which you can start depositing salts. And it builds up crazy from there. So we actually did some experiments like that. We, in one of our experiments for a master's thesis, we had a cube, 4 sides, and we etched microchannels on one side. We completely smoothed the other side. We did random things on one side and a different microchannel on the other side. And we put this thing in the same solution, and we examined how the temperature fluctuation was, what the rate of salt deposition on this was. The one with microchannels, at first, it has much better heat transfer rate. It helps a lot. But when you keep operating on that, you keep building salts on it, and then that starts hindering your performance.
Gotcha. Okay, next question we have is, are 2 of the major controls for lithium recovery in the atomizer adjusting airflow and setting heat exchanger temperature? If so, is it more important? And what impact does changing each one have on the recovery?
Excellent question. So I was given a talk to some potential investors at 7 a.m. today, and one of them asked the same question, is what are your knobs to control this, and what are the impact of those knobs in doing this? All right, so I'm going to go on this slide. Yes, we can change the temperature, we can change the flow rate, and there are a whole bunch of chemical things that we can change. One by one, changing the temperature, just scientifically, if you look at your vapor dome, this is your vapor dome, you go up in pressure, the part of the vapor dome in which you are, basically your latent heat changes based on the pressure. So we can pressurize the system a little bit, go up on the vapor dome, and help reduce some of our energy need. The downside of that is now you need to pressurize the system, and pressurizing the system costs energy, costs work. It also means that after a certain point, you start having to change your materials of construction for the chamber because they need to withstand that pressure. Airflow. Excellent question. Airflow is one of our bigger sources of energy. So if you want to have more airflow through the system, it does great things. It changes your thermodynamics, sometimes for better, a lot of times for better by reducing your temperatures. Increases the momentum through the system, so it helps with salt separation. But also the cost and energy of compressing that amount of air and displacing that amount of air starts adding up rather quickly. So we need to be very careful about that. And there's things about pH control and chemical adjustment, and adding those compounds, there's cost there. Getting them out of the system eventually when their job is done, it's another cost of the system. So in short, yes, we are actively doing thermodynamic analysis and thermodynamic optimization of our process, including airflow adjustment, pressure adjustment, temperature adjustment, and chemical adjustment. And all of that is linked to our techno-economic analysis to see what has what side effect on the controls, on materials cost, on fab cost.
All right, perfect. We have time for one more question. Are you hiring, and how can people get involved?
Excellent question. We are hiring for 3 positions. A CEO to replace me at some point down the line, a senior research engineer, someone who has a doctorate in areas related to thermofluid sciences, and also an entry-level technician, because the more you start doing this, the more you realize to build a technology, you need, like I said, an army. People who do not necessarily have advanced degrees, but they're a wizard in the lab, they can build things. Entry-level engineers with a bachelor's degree who can do a range of things, masters and PhDs and finance people and tax people, a lot of things. So yes, we have an open position, and if you're interested, please do reach out to me, reach out to contracts@spq.com. And I just want to end on this note that in addition to all the students that I showed you, there are a lot more of them. And 2 of our key employees right now are 2 former undergrad students who stuck around and are doing a fantastic job building this technology.
Thank you again, Professor Abbasi, for this fascinating lecture and for your answers to all the questions. Before we go, do you have any other parting comments you'd like to share with the audience?
No, thank you all very much for the great questions. Thank you for the participation. Thank you for doing such a great job moderating this, and for everyone involved in this. It's been a journey, it continues to be a journey, and Oregon State University is the ideal place to do this because of the quality of the students, because of the quality of all aspects of the university, and the commercialization office who has been, and the research office who's been a wonderful partner through all of this. So thanks to you all.
Thank you to you all again in the audience for joining us today and for your great questions. As a reminder, we will be emailing you a captioned video recording of the lecture. We also hope you'll join us for the future College of Engineering faculty lectures. You can find a link to the full schedule of all upcoming lectures on the page for today's event. Thank you again for attending, and have a wonderful afternoon.